Okay. Any questions before we get back into the material? I know there was some homework questions that you guys talked to during lab, which is perfectly fine. I told Conlon that's probably going to be the hardest, like most challenging, because it pushes your thinking, especially as an electrical engineer. It's the hardest in terms of understanding the concepts. So I expected questions, but we can go through questions now if you have any, or the homework's due today, right?
Yeah.
1 minute. Oh, I have 8 o'clock, so.
Yeah.
So any questions on the homework or anything, or?
Yeah.
Yes, there'll be at least one. Yeah.
And then also for the last one, like,
The last problem?
yeah, you tend to find -3 and -7. I find
I thought it was -3. Didn't I say -3 and -5?
-3 and I find it different.
Well, let me see. That was number 3.
So the last one, I think.
No, homework number 3, right?
Oh yeah. Oh, yeah, no,
It was homework number 2.
yeah. So they're talking about the
I thought it was this one.
this one, yeah.
Yeah, this is homework number 3.
I didn't even find the title like it.
So here's what I got. So to do this problem, and I didn't even tell you to derive K effective. In the past, I've said you got to actually solve for K effective. And when they're in series with each other, they look like resistors in series, but they're actually treated as resistors in parallel, because if you think about it, if this point right here, so you can do our free body diagram, if that point is moving in this direction, so this is the direction, X is going here, K2 is being elongated, right? Which means it doesn't want to elongate. It wants to go in that direction. It wants to stay in equilibrium. K1 is being compressed. So it's going to potentially push back in that direction. It just depends. And so what ends up happening is you end up with all these different conditions where it may or may not be helping you. And so you actually just treat it as a resistor or resistors in parallel. When they're over here and they're on opposite sides, this is when they're adding in series. Okay. So that's the reason why we do the K effective. But with that being said, all you had to do was look at the denominator. So S squared plus B1, B2, 32/4, right? Times S, which is 8. Plus K effective over M, which is equal to the product over sum is what I ended up doing. So the product is 24 times 20, which is, let's see, that's 480, I believe, if I did that correctly. And then over the sum is equal to 44 times 4. Can't do that. Well, I can kind of do that in my head. So that's going to be equal to S squared plus 8S plus 4. So 480 divided by 176. I definitely can't do that in my head. So let's do that over here. What did I say it was? Just bear with me. 480 divided by 176. Nope, I must be doing it wrong. Let's try doing that again. So let me do product over sum. So it is K1 is 40 times 24. Oh yeah, I'm looking at the wrong numbers, so cancel that out. So it's product over sum. So K effective is going to be equal to 40 times 24 divided by 64. What's that? I added it internally. So then K effective equals K effective divided by 4.
Yeah.
So 3.75. Now I just have to do the roots. So you're right, I must have not divided it by 4. So minus 7.64 and minus 3.6.
Yes.
So minus 7.4 minus 0.36. What's that?
So those answers are correct.
Yeah, I had minus 5 minus 3. It's minus 7.4 and minus 0.36.
I was wondering about that as well. It asks for omega and zeta at one point, and in the slide it has what the form would be. With that in the numerator it has omega.
So you're talking about like that, right? So what you're saying is there's no omega sub n over here? I can make it have omega sub n. Remember how we did partial fraction expansion when we had signs? How'd you get omega in the numerator? You multiplied that term by omega, and then you divide by the omega.
Use the controllers.
Yeah, you just move it out front. Because why? This is a constant, it just moves the amplitude up or down. It doesn't actually impact the partial fraction expansion, just an amplitude adjustment. It's multiplying by a constant. So you can have whatever you want up front and it doesn't matter. Barzilli kind of asked the same question saying, do I need to multiply that by s squared? And you don't. It's just moving it in the constant. What is the most important part for doing partial fraction expansion? Is that number is a 1, right? We always want the s squared term to be a 1. Now, I will say we have to modify that when we get, if we do Bode plots in this class, we actually don't want that to be a 1. But almost all the other cases, you want the highest order s term to be multiplied by 1.
Yeah, can you also do the bubble? Oh, this one, yeah.
Sure.
No.
That what?
The V in, so V in goes in, and then minus plus goes to ground.
Yep. So let's see. So this here, this is going to be ZF. And this is going to be, we'll call it ZN. Now I have to think about this one. So let's see. Give me a second to think. So my current here, I know this is at ground potential, right? So this is at 0 potential. Well, because of the ground right here. Let me think.
You know what the resistor right there, probably that.
What's that?
So the resistance between V in and that node. Up to the work out.
Yeah, but it should be able to still work out. Oh, it's actually easier than that. This ground and that ground. Nope, they're not in parallel. I was gonna say they're not in parallel.
The all the ground, got it, and like, this doesn't put it, so that's
Yeah, it's across the Z1, this is here.
V1. Then it's ground. Going radial ground.
Yeah, let's see if I have my notes in my homework-free solutions. I don't know, I'll have to get, how about, oh, I don't have my solution part here. So what I'll do is I'll go back and because I need more time to think about it. I don't want to spend the time. So what I'll do is I'll go back and then I'll post how I did it. I'll just post it to Brightspace. I can't remember how I did it, so I gotta think about it for a little bit. Yeah, then you can drop it that way.
Yes, and that would definitely be very nice, because then you add like the inverse which add the two voltage, which adds 0 and
Yeah, so it makes sense. So if V in is tied to the terminal. But I'm wondering. No, it should be 0.
Even though the resistor delta, the R1 symbol will be useless for the meter.
Right, because all it would be for filtering purposes, it doesn't really
Yeah.
matter, because it's still ties it to ground, so it would be at 0, so 0 to 0 is ground. I don't know, I'm gonna have to take a look at it and get back to you, I can't remember. So I have to think about it. So, like I said, let me get back, I'll post it. Okay. Any other questions? Oh, what I did?
Yeah.
Well, sure. But you can also see. Hopefully this is available now. Oh, I'll change it to right now. So I did create this morning, and I apologize. I should have done the other one, but I have created a homework solutions. And I'll just make this available now. I was doing my other class this morning too, and don't want any of that. I just want to update. There we go. So now you should be able to access it, but we'll also look here. Number one, the easiest way to do it, in my opinion, is just take everything to the Laplace domain. This is unity, right? This is a unity buffer style one. So that one should make it pretty easy. So you can see I do the process where I have a voltage divider. So I'm just looking for the voltage across here. Right, and that's going to be reflected to the other terminal. So I do a voltage divider, and then that gives me it referencing it to V1. That's my input. And then my V2 is just going to be equal to my V in, essentially with my unity gain buffer amplifier that I have here. Continue on, I've got my V3. Same process, I've got to do a voltage divider here. So that's the way to start these problems, just do voltage dividers. And then once you have the voltage divider, then you know the terminal voltage, and you can go ahead and set the output voltage that way. Okay. So it really was just doing voltage divider circuits across there. That's what this part is right here. That's a voltage divider. And since it's a unity gain, V1 and V2 are the same, or buffer amp, right? This connection right here means V1 is there, which means it's there. Does that make sense? You guys have done buffer amplifiers in previous circuits classes. If you haven't, a buffer amplifier, the whole purpose of a buffer amplifier is it just, so the ultimate reason is it just takes whatever input it is and moves that to the output. And you can say, what's the point of that? Well, because it creates a buffer between stages. So it gets that really high input impedance and really low output impedance. So you can decouple the stages between the two. That's why it's called a buffer amplifier. Its whole purpose in life is to provide separation between the two stages so that you can get good operating characteristics without worrying about interstage loading. That's the quote unquote buffer part of the amplifier. So it was literally just a bunch of voltage dividers. This problem was way easier, hopefully, than one would imagine. It wasn't meant to be a tricky problem. It was just meant to be like, oh, I have to do voltage dividers. And what I was really asking you to do on this problem was to recognize that V plus is the same as V minus in ideal op amps, right? Just because we don't tie it to ground, that rule doesn't change. So instead of it being at 0 volts, it's actually at V1. But what is V1? It's just a voltage divider. Yes, sir.
Can you do this problem? Try to do it with outputs.
You mean,
Just looking at current, so.
sure, current analysis would work. I don't know if it would save you a lot of time.
No,
Take what you did.
Oh, does it?
there'd be no flow from B1 to B2, right?
From V1 to V2? Well, no, they're at the same potential. Why would they be current flow?
Or even to B3, I guess. From B1.
There is a small amount of current, right? Because you do have a voltage divider network, so you do have a voltage drop across C2 and R2, right? You can send current through here. That's why V2 and V3 aren't the same. If there was no current, then what would V2 and V3 be? They'd be the same. So you have to have current flow through there to be able to get a voltage drop. But yes, you could do nodal. It's just that, to me, it just screams voltage divider. You have a series circuit with two elements. It's like the perfect opportunity to take advantage of voltage divider. So a couple voltage dividers. This one, I gave you the K1, the K effective. So all I did was combine this into one, and then you did your free body diagram for the mass. You apply a force in that direction. The spring's going to be this way. The damper is going to be this way. Same thing with B2. B2 just opposes velocity. So it's going to oppose. And then the last one I have for opposing forces is the mass one. This one is F of T. So if you do your free body diagram, you have four forces opposing your applied force. So that's this equation here. Then you just took it to the Laplace. Yes, sir.
That's the. Here the similar spring, if you have two of them in series, they are parallel.
Yes, same thing. Yep. But you probably wouldn't have two dampers in series with each other, just because you're working with different velocities. And so now it really complicates your equation because we've done everything in terms of position. Now you have different velocities. Now you got to start taking different derivatives. So now you have to add another distance point, where for us, we can just go ahead and simplify that with that one point. And then number three, you just did your free body diagrams with torque. So for this one, you have a T applied over here. You have a B1 in this direction that's opposing it. You have the mass for the moment of inertia going this way. And then you have a coupling between two separate masses. And unless that's a rigid object, you can have some twist in it. And that's considered a spring. That's represented as a spring. So maybe instead of a rigid object, it's made out of rubber or something like that, that gives you flexibility. Yes, sir. Say that again. Oh, going back to number two. The poles, all I did was the roots of this equation here. Is that what you mean? This other part is omega n. That's a second order system stuff. I have some equations. I probably skipped ahead a little bit, but all the equations we would cover today.
Oh. I think I'm correct. So you said that the applied torque, the of the second mass, or thinking only have to do for the second mass.
So if you read it carefully, I'm looking for a transfer function relating applied torque, which is over here, to the speed of this over here. So I was looking at the input to the output all the way through.
Yeah, I think it's right. That's the one.
Okay. And so now we have a spring, and remember, the force is going to be if theta 1 is moving faster than theta 2, it'll be in this direction. So that's K theta 1 minus theta 2. And that's it for that mass. Going in this direction, we don't have any applied forces. So all we have are just opposing torques. So I have B2. I have J. And the only thing is my spring here, now I want the torque to be in the opposite direction. So I want it to be going up. So now theta 2 has to be rotating faster than theta 1 to get the torque to go this way. So that's why it's K theta 2 minus theta 1. Yes, sir.
So you're just saying that theta two that can rotate faster than one. So why don't you do for the B two, why don't we multiply that by theta two dot minus theta one? Why is it just theta two?
Because what is the movement is just what is, we're assuming that this spring only exists between these two. We have to basically lump it onto one side. So actual J is rotating at the mass is rotating at theta 2 only, and that includes this friction. Otherwise, you have to distribute that K term over different parts, and that would be too difficult. So the K, that's why the K is represented here to the left. So it's the object, it's the spring between those two, and move B2 to the other side. Okay. It would make it almost impossible, because then you'd have to know where is it on the shaft and how far is it over, and is it 30%, is it 50%? So everything is lumped and moved on to the left-hand side.
But back on question 2, why?
In the first problem, or the problem we talked about, what always multiplies S? The highest order S term. Has to be a 1 there, right? So we have to divide out the M in the denominator so that the highest order S term is only multiplied by 1. That's why we factored it out. And what we'll see is this is the standard representation of a second order system. You can see that the S squared term is multiplied by 1 in that case. Any other questions? I owe you a response on number 4, but any other questions? A lot of practice problems, a lot of op-amp stuff. And only a couple of mechanical systems. Yeah, so I've got to finish putting the test review together. And so the test is going to be a week from this coming Wednesday during lab. So Conlon, we're going to do a review session on that Wednesday, and then we'll also do a review session the following Tuesday to answer any questions. So it'll be up to including everything that we covered on the last class. We won't really get into second order systems. We'll wait to do that in the next exam. We could actually have an exam next Wednesday, right? But I didn't do that. Anybody want to raise their hand? It's in 321. So a fair number of students. And I have a Monday exam in 321. And I thought, to be kind, I didn't schedule 2 exams for them in the same week. Anybody have a problem with that? You have a problem with that?
Oh,
Yes, that's a midterm. So that's going to be like in the middle of the semester.
there's no class.
It wasn't?
Also, homework.
The what?
Homework.
Today?
Yes, just make sure.
So if you have a directory, how do I take a picture? All I do is this. I do the snipping tool. And then I do my directory. I like the snipping tool. Yeah. Right here.
You hit save. You gotta hit save, bro.
You can hit save, or once you've got it here, you can actually start. Let me make sure I don't have any exams. I do, so. So now it's just in your clipboard. So you can go ahead and you can copy it and paste it. Yeah, you can I use the snipping tool, but Control S you said works well.
Windows, Shift.
Okay. Yeah, I use the snipping tool. I just leave it running all the time. And then I can see what I had. This is all we're looking for. But I'll double check why I didn't get the Tuesday one. Could have sworn, I can just bear with me, sorry. Well, I'll do it after because it'll take me a few minutes, but I'm surprised that I didn't do that. I'm pretty sure I got the class from Adam, but I know he didn't post it, he didn't get it to me before the actual class. So I couldn't get it at 4 because it wasn't available. He didn't send it to me, the link, until after 5. And I thought I had processed everything and put it on there, but maybe I didn't set it up. It's delayed or something like that. I don't know. I'll have to take a look, or maybe I put it in the wrong spot and make sure. But if that happens, just let me know in advance to say, hey, is there a class yet? You didn't have to wait till today. You could have just said at 5 or 6 o'clock, hey, because usually they're supposed to get it to me before like noon of the day. And that way I can process everything and get it up to date. That's the thing about working with a class like this, right? Because I'm not presenting it. I'm relying on other people to give me the videos and stuff like that. But the good part is, nobody's going to argue with these people as saying, hey, is this the right thing to do, right? These are all people who are currently working in the industry and know their stuff. So it's kind of the catch-22, right? You're getting real world stuff, really knowledgeable people teaching this stuff, but I'm at the whim a little bit of like, well, they get it to me, they get, there's no penalty, they're doing this for free. So, there's not much I can do in terms of saying, is there any way you can speed this up? So it's it is what it is. But I can fix that after class, so it shouldn't take me too long. Did you guys get graded on your homework already for homework number 1? Yeah, so I sent that out to Leo, but he's got 2 little kids, so I'll have to ping him. He said he was gonna get it done already, but yeah. Yeah, I have to grade some of the homeworks, and then normally the instructors will grade it. Like the next batch of stuff is all, if you remember Pascal or maybe even Jude's area, it's not my area, so I would struggle to grade that. All the other material, I know it pretty well, but the stuff that is coming next is the next 3 lectures is not my bailiwick. So anyway, we're getting sidetracked. Sorry about that. All right. Second order systems. A second order system is one that consists of first order systems, but you can't necessarily break down those systems into components that are real when you do factoring. That you'd end up with a real part plus or minus an imaginary part. So that doesn't work, right? That's not effective. So we're going to come up with a whole new set of rules to analyze second order systems. And hopefully it makes a lot of things make more sense, especially from a design perspective. So we apply our quadratic equation and we have any function. And the question that Drew asked is, B is still there, right? But I can have a 1 over here, and I can just move the B term up front. That doesn't mean there isn't some constant out front either. This is just what the standard form looks like, because we would go back to the table. So if you don't see B in the numerator, don't worry about it. I really only care about the terms in the denominator. I can make the numerator term work. I can't make it work in the denominator. So if you have an undamped system, which means there's no resistors whatsoever, there's no real part, there's no exponential decay, because if you recall, this part right here corresponds to that e to the minus alpha t term. That's the decay part. This term, if it's complex, is the radian frequency of the sine or the cosine wave that we're going to end up seeing. So if A is equal to 0, no damping, all we end up with is this square root of B. That term is so important to us, we come up with this expression called omega sub n. It is the undamped or natural frequency of our system. So like the case in a crystal oscillator, you're designing a crystal oscillator to have as little damping as possible. That's what you want it to go forever. And basically you excite it and then it just oscillates forever and ever and ever. That's how computers used to keep track of time. Does anybody know if they still use oscillators, crystal oscillators in computers? They don't, or you don't know?
I know they use ports.
In watches, yes. But what's the difference between computers and watches? The what? Yeah. So in your time and date, they actually, as long as you have an internet connection, Microsoft will go and update. I don't know how often they do it, but they'll go to the atomic clock calculations, and then they will adjust your time automatically. It used to be, it wasn't that long ago, 5 years or so ago, that your computer kept track of time internally. And that was a crystal oscillator that was always running, and it was bouncing back and forth, and your computer never really shut down. It was actually keeping track of the actual time that way. And that was all done with a really small battery inside your computer. And so it would oscillate, but there's no such thing as zero damping in the real world. So there was that battery just to keep it oscillating at a certain frequency. And what would happen is that battery would eventually die, and then your clock, you turn on your computer and the clock would be, zero, be midnight at some random date and time because you lost your clock. And sometimes you could replace those, sometimes you couldn't. So we're going to introduce this new term. We're going to call it zeta. And I know it's a squiggly, crazy letter, and you'll see it change a lot, but it is just whatever the term we have. And this is going to be defined as the exponential decay divided by the natural frequency. So another definition that we have, exponential decay divided by natural frequency, which means we can substitute in our equation for zeta to be equal to that natural decay, which is a over 2, divided by omega sub n. And then we can say that our a term is equal to 2 zeta omega sub n. So now what we see is we can rewrite this expression. So we always multiply this by 1. If we have no damping, whoops, this should be an S term here. If we have no damping, then this term 0. And then all we're left with is omega sub n squared. So this is our standard form for a second order system. 2 zeta omega sub n s plus omega sub n squared. And you can equate terms. This is A and this is B. So you always solve for B first and then solve for A. Does anybody know why? You need omega sub n, because if you don't know omega sub n, how are you going to solve for zeta, right? You need that additional term. And so most of the design stuff we talk about is we want a system to have a damping ratio no greater than X or no less than X, so we can go ahead and have our system respond as we expect it to. So now we're going to substitute that into our equations, and we're going to end up doing quadratic equation, and we end up with our poles are now negative omega zeta omega sub n plus or minus omega times zeta squared minus 1. There's a little bit of math to make this work. It's not hard math. It's just a little bit to make the formula work out. This is important to us because remember, this again should be J. I don't know why I have so many typos. Sorry about that. That's plus or minus J times omega sub n. Here, I can fix it. I can fix these right now. This has to have, oops, what happened? This term right here, I need my S. And then I need my J right here. All right. So getting back to it, this is an important term for us because you'll notice it has omega sub n, which is our undamped natural frequency of our system. But it's multiplied by something, square root of omega zeta squared minus 1. Okay. So if our system is damped appropriately, then omega is going to be less than or equal to 0, right? Actually, let me fix this completely. Hold on. This will make a lot more sense if I fix this completely. I'm going to just move these around. 1 minus. So if zeta is less than 1, what is zeta squared going to be equal to or less than? Isn't zeta going to be less than, squared going to be less than 1? So this number, 1 minus something less than 1, is always going to be greater than 0, but it's going to be less than 1, isn't it? So what does that tell you about omega sub n times 1 minus zeta squared? It's going to be less than omega sub d. I mean, omega sub n, right? Always going to be less than. Wish my erase button would work. Always going to be less than omega sub n. So if omega sub n is our undamped natural frequency, what would this term be? Kind of gave it away when I erased the d. It's the damped frequency. So this is undamped, this is damped. So when you add, if you add damping to your system, so if that S term, that 2 zeta omega sub n is not 0, your frequency is going to be lower. You're going to have a lower radiant frequency. So that is why we call this our damped frequency, omega sub d. All it does is dampen the turn on. Okay? Questions on that? Because now you have the equation for zeta, which we've already said, right? Because 2 zeta omega sub n equals A. So A over 2 omega sub n, you know how to solve for that. Omega sub n is equal to B, and omega sub d is equal to 1 minus zeta squared times omega sub n. And what we're going to do is we're going to start developing equations based on all these coefficients, particularly zeta. Zeta is really helpful for us to design our system. So let's look at 3 cases. Yep, sure. A over 2 omega sub n, yeah. 3 cases. Zeta is greater than 1. Zeta is less than 1, but greater than 0. And the last case is zeta is equal to 0. So if zeta is greater than 1, what ends up happening here? Do you have an imaginary term? So what does that tell me? An imaginary term times an imaginary term is a real number, isn't it? So if I have an overdamped system, I don't have oscillatory response. I'm just going to have 2 real roots. And this is just going to be regular exponential decay. This is going to be an e to the minus 7.9 t. And this is an e to the minus 1.1 t. There is no sine and cosine. So an overdamped system is one where you put in so much resistance to your system, it doesn't oscillate. It reaches its steady state value without any oscillation. And we see that here. You see that this system, when we have C of S equals 9, and I've hit it with a unit step input, S times the system transfer function, and I take it back to the time domain. This is my forced response. These 2 are my natural response. And I can see on the output, when I run it through my C of T, there's no oscillatory response here. And I also see it maybe even more clearly look at my whole zero map. I don't have any terms that have a J term in them. So I don't get any oscillatory response. So an overdamped system has no oscillation, which might be a good thing or it might be a bad thing. One of the things to consider about oscillatory response is it's kind of doing one of these things, right? It rings until it reaches its steady state. So in a case when you have some oscillatory response, you have some overshoot here. You overshoot your steady state value. Is that a good thing? Is that a bad thing? It normally is acceptable to have some overshoot as long as that overshoot isn't too significant. If I'm filling up a tank and I want to get to 50% full, I'm okay maybe going up to 52 or 53% and then coming back down and then going back up and then eventually settling at 50%. Anybody want to guess as to why that's okay? What's that? Sort of. This system over here takes 5 time constants to reach steady state. And the 5 time constants is the slowest of these two. Which is the slowest of those two? Is it the first one or the second one?
What do you?
This system, right? We want it to get to, we want the water level to get 50% in our tank. That's what the operator's saying. They're making a set point adjustment to go ahead and get 50%. I want that to happen. Am I okay with it getting there and overshooting a little bit, then getting to 50%? Or am I okay with it getting there without any overshoot? So then the follow-on question is, which is the slowest? Because it's got to reach steady state, so both of these have to decay away. Which is the slower of the two? Which takes the longer amount of time to decay to zero? We did this on Tuesday, remember? One close to the center. Everybody agree? Refresher. How many time constants does it take to get to steady state? So what is greater? 1 over 7.85 or 1 over 1.17? Say it again. That's like a 10th, right? This is almost a 20th. So 5 times a 10th is slower than 5 times a 20th, isn't it? Still confused about that part? A little bit? Let me spend a little more time. That's okay. If it's not sure, we'll spend the time. So what we get out of our expression is e to the alpha or at, correct? But us electrical engineers, we love to work with e to the minus t over tau. Why do we work with that? Because we know that when tau equals 1 time constant, or the time actually equals, let me back that up. If the time equals 1 time constant, we know that this is e to the minus 1, correct? If t equals 2 time constants, it's e to the minus 2. If t equals 3, let's go all the way to 5, which is essentially 0, right? So it steadies out in 5 time constants because t is equal to 5 tau. When I divide 5 tau by tau, I just get e to the minus 5. So by doing it this way, it screams at me how long it takes to get to steady state. Over here, that's a lot more confusing, isn't it? When I see e to the minus t to the a, because how long does it take to reach steady state? It's not as obvious, is it? But over here, all I know is when t equals tau, that's minus 1. When it's minus 2, it's over here. So now what I need to do is I need to make this equal this, correct? So let's do some math. Take the natural log of both sides. Divide both sides by t or minus t. Solve for tau. So we just have to invert whatever our coefficient is.
So in that example, when you're looking at the whole zero map, that's your A. But it seems back.
Say that again. This is A right here. So then I do 1 over tau and 1 over A, I should say. And so I end up with a smaller number. So this reaches steady state faster. The further it is from the j omega axis, the faster it reaches a stable point. It decays away. No, I said tau. I said, what is the smaller tau? The smaller tau reaches steady state faster. I think I said that. Maybe I misspoke, but the tau, the smaller the tau, the faster it reaches. But the larger the A, the faster it reaches. See? Because it's the inverse of each other. Go back to this, right? So if I want tau to be little, what does that mean for A? A had better go up. Does that help at all? You can say no. The pole at -7, whatever it was, because that results in a bigger number, because 1 over 7 is going to be less than 1 over 1.1. Make sense? That's why it's helpful to do this tau stuff. It kind of brings it all together, in my opinion. So this is going to take this much time, right? So whatever that inverse times 5, it takes that much time. So it takes that to reach steady state. Let's go to the next case where I'm going to be between 0 and 1. I'm going to be greater than 0, but less than 1, essentially, okay? Now what ended up happening is I actually have damping. So if I go back over here, if this is less than 1, this j term doesn't cancel out, right? So this is a complex number, which means my output waveform has a sine component in it. And when I plot that, I can see I get overshoot. And it steadies out in a certain amount of time. So the question is, which one is faster for reaching steady state? Underdamped or overdamped? Which would you rather do? The underdamped case or the overdamped case? They're the same?
It depends on the application.
Depends on the application. And that was one of the caveats I said, right? Depends on how much overshoot you have. If you overshoot by 80%, that might be a bad thing. But if you overshoot by 20%, so instead of at 50%, maybe you're at the 60% mark, that might be tolerable. But yeah, which would you rather have? If the tank wasn't going to overfill, which of the two would you rather have? All things being equal. Underdamped? Why? It's a little nicer. I have one overdamped and one underdamped. Anybody else want to stake a claim?
Is the only difference just your data? The rest of your system is the same.
Well, the transfer function is different now because it is s squared plus 2s plus 9. It was s squared plus 9s plus 9. So the transfer function looks different. And I tweaked something. I put more resistance in my system. So maybe to fill that tank, I put a flow restrictor or something like that to limit the amount of flow. It resists how to fill that tank. I would want an overdamp because I will have a larger A. What is the famous expression that everybody uses about finances? Time is money. Which system takes longer to reach steady state? Underdamp takes longer? Well, to me, this, what's that?
-1. Where this.
So we said that this is going to be -1, right? The slowest system is going to be minus 1.1 over whatever that is, right? What about over here? This system reaches steady state faster than the overdamped system. So if you can compare, you know, it's somewhere between 4 and 5 seconds where it reaches steady state. Over here, it's hard to see, but I'm a little bit closer to achieving steady state with the overdamped case than the underdamped case. If you do the e to the minus t and you do all the conversions, you're going to reach steady state faster. So the K is faster than the other one. So this is a more rapid response. So the underdamped case between 0 and 1 is going to give you faster response. As long as you can tolerate the overshoot, you're good to go. What about undamped? Never gonna, it's always gonna try to go to 50%, then 100%, then 0%, 50%, 100%, and 0%. This is a really bad case where we don't want to necessarily be there because we have no decay. So you never want a second order system that's undamped unless you want a crystal oscillator, then you're allowed to do it. And you never can get a truly an undamped response. It's not going to work. We're going to add one more case. I said 3, but let's add the 4th one because really what we never have is undamped response. Let's look at case 4. What about case 4? We have 2 poles at that location. And this is the fastest system we get. It reaches steady state the fastest. Critically damped means zeta is equal to 1. So you have 2 poles that are real and are the same. So you have S plus 3 squared. So in the critically damped case is the fastest system. There's one problem with the critically damped case. In the real world, things change, right? Things move over time. So this pretty quickly will move to an overdamped system, most likely overdamped. They usually increase resistance. They usually don't decrease resistance. So you normally will have a critically damped system. So if you tune it perfectly, it's critically damped. And then over time, it begins to become overdamped. And then you have a slow responding system. So if you were designing a control system, you normally want an underdamped system because as you increase resistance, as long as you're not so close to the edge, you're still going to be a faster response. So critically damped would be ideal, but in the real world, it doesn't happen. So you go with an underdamped case because it's going to give you steady state, usually the fastest or close to steady state, right? Because it rings forever. But in reality, it usually takes 5 time constants. And so we'll assume that any transients decay to 0 after that. And what we end up having is the fastest response. And there's all kinds of work analyzing underdamped systems to tune them. So when you do a bump test, you actually want a little bit of overshoot in your system to go ahead and get the system to respond the fastest. So case 2 is the best one for us. Okay, makes sense? Kind of, sort of, maybe. Yes, no. Sort of.
I was just confused by the S pointing there, where the poles were at -1. In the, overdam cases, closer to making 8. But can you not draw a comparison there? You just have to look at it.
Yeah, because remember, what we say was the slower of the two? Is it 1/7.85? Or is it 1/1.146?
The slower is the 1/1. 1/1.
1.1 is slower, right? So that takes a longer time. So this is the one, that's what we call a dominant fold. It dominates the output characteristic. Because this one is doing its thing, but it's going to decay away fast enough. This one is going to be the slowest, and we need to consider that. We need to figure out how to manage that. Okay. So those are our 4 cases, and you can see that here all overlap on each other. You can see the critically damped. Look how fast it reaches steady state. It's over here. And then look at my underdamped system, which, again, it's hard to tell, but it looks like it's meeting this line right about here, which is faster than the overdamped case, which is someplace out over here. So if you have a need for speed, this one is the one that you're going to go with, because this critically damped, as the system changes over time, moves to an overdamped case, and then you get a slow characteristic, slow response. Okay, so those are the 4 cases all represented. Again, we really can throw out the undamped case because it doesn't really do much for us. It actually causes a lot of problems. So we almost never include it. We really will focus on the underdamped case. If you need the other one, you're good to go. But underdamped, kind of a summary. You have your roots is a real part, plus or minus an imaginary part. If it's overdamped, your roots are A1 and A2, and they're both real. If it's critical, your roots, you always have 2 roots. You have 2 real equal roots. Okay, overdamped, you have 2 real and non-equal roots. Underdamped, you have 2 complex roots. All right, pretty important that we see those. Okay, so here's an example. What am I doing for time? I get time, good. So here's our system. We have a transfer function, 12 over s squared plus 8s plus 12. Now what we want to do is we want to solve for our zetas and omega sub n's. So the first thing we do is we pull out our b coefficient, right? Because this is a and this is b. And we know that b is equal to omega n squared. So we solve for omega n as being equal to the square root of 12. Once we have that, then we can solve for a by dividing our our a term and dividing that by 2 omega sub n. So 8 divided by 2 multiplied by square root of 12 is actually greater than 1. So this is an overdamped system. And we have that. Yes, sir.
We always assume that omega n is positive with the square root of the number.
Yes. What? Excellent question. So for those who can't hear in TV land, Drew asked the question, does this always have to be positive? And the answer is yes, it does. And I will ask you the question, why? Could that ever be minus? The answer is, what's that?
Yeah.
Well, if it was a negative number, not necessarily. It would be an unstable system. And an unstable system, you're not even doing this work because it blows up to infinity. So any negative number, anytime you see a sign change in the denominator, so if all of these are negative, it's one thing, but if you have positives and negatives, it's an unstable system. You can try it. go into MATLAB and do roots and do whatever you want. We'll actually see that. We'll derive that later on, but you'll never see a negative number in that denominator, and it'd be a stable system. Yes. If it's marginally stable, excellent question. If it's marginally stable, don't you have this? An undamped system, right? Two poles, two complex poles, or two poles that are on the j omega axis means there's no real part for your exponential decay, which is another way to say there's no damping. Right? What you would have, isn't that a marginally stable system? For a second order system. Can you have this and analyze it? Sure, but it's not a second order system. It's one pole, right? At s equals 0. So that is, we don't do any of this work for second order systems. This is only if you have an s squared there. We have an s to the 1 there. So we don't have to worry about that for this work. But marginally stable means undamped, no damping whatsoever. Okay. So now we'll have to do a little bit of math, and we can actually do some plotting, and you can see that the less damping you have, the closer and closer you get to a critically damped system. So if zeta is equal to 0.1, which is almost no damping, right? Your damping coefficient is 10%. That's really low. So it oscillates wildly, and it takes a fairly long time to reach steady state. You can see how it oscillates. Then we go to 0.2, better, right? Less overshoot. And it takes, whatever time it takes to reach steady state. And then we can see we plot all the way up to 0.8, which has hardly any overshoot. And then you can see that it reaches steady state in a reasonable amount of time. We don't have 1.0 because, again, that would not be any damping. That would not be an underdamped system. That would be an overdamped system. Just some general formulas too. If you have all the parameters, you can go right to the time domain for any second order system using these equations here. This is the easiest equation to work with. Do it that way. I know it looks like a lot, but believe me, the equations get crazier before we're done with this material. So let's do those equations, those crazy equations. We have a rise time, same thing we did for first order systems. The amount of time it takes to go from 10 to 90%. That's shown in this plot here. And we've already discussed why it's 10 to 90%. Now we have to add one term here because in a second order system that's underdamped, we actually overshoot our final value. So now what we need to do is add another time, which says this is our peak time. How long does it take for that peak overshoot to occur? So we calculate our peak time using this equation over here. Okay. Now our percent overshoot, this is the actual value it gets to, and this is a percent overshoot. So what that means is you have to normalize it. So if this is equal to 1, then, and this is 1.4, your percent overshoot is 40%. If this is 10 and it goes to 14, it's 40%. If it goes from 10 to 10.4, right? That would be 4% overshoot, wouldn't it? It's a lot less than what it is. So just make sure if you do percent overshoot, you recognize that you have to normalize that to what the steady state value is. Don't just plug the number in. That's a common mistake that students make. Is there a question?
Yeah, you compare you compare the final to the overshoot, or you compare?
Final to the overshoot. So what the steady state value is, and then the percent overshoot is how much higher it goes to that final value as a percentage. And how do you find the final value? And use the final value theorem, right? If you don't know what the final value is, just use your final value theorem and you can go from there. Most of the time, your design specifications will say, I want my percent overshoot to be 30%. they won't oftentimes say, I want my overshoot to be no more than 15. Because then you'd have to know the values are and go from there. So my equation, this is where the equations get crazy. Percent overshoot is E to the minus zeta pi over 1 minus zeta squared, that's square rooted, times 100. Okay, that's the percent overshoot calculation. And this is one we use all the time in our design. Can anybody tell me why we use this all the time? If you look closely on the page, you have 3 equations. If you compare those equations, you'll notice something very different about percent overshoot. Can anybody guess as to what that is or see what that is? Look at the 3 equations. What's unique about percent overshoot equation?
Oh, no.
Yeah, no omega sub n. So it's the easiest one because you can directly calculate zeta from it. So you oftentimes will calculate percent overshoot and use that first because you can immediately pull out what your damping ratio needs to be greater than. Okay, the other ones you need to know zeta or omega sub n to be able to calculate those. So normally you'll be given two design criteria. I want my percent overshoot to be less than 30%, and I want my settling time, 2% settling time, to be 5 seconds. If you have those two, you can design any second order system. Here's my settling time equation. TS equals minus ln of 0.02 square root of 1 minus zeta squared over zeta omega sub n. Okay, don't need to do the derivations, takes a lot of time. And then we already talked about, whoops, this is a typo. This is omega sub n, so we can fix that. This should be omega sub n, not omega sub d. And this figure here is very important to us, especially if we start looking at root locus. So I included, it looks like a lot of math, but when we actually start doing plots of pole zero maps, you're actually going to see plots, so like literally lines of them. You're going to see why having this plot over here is really important. So if I recognize that my damp frequency is this equation here, then I can go ahead and I can write on my pole zero map my coordinates. I know that this is the omega sub d term, the plus or minus omega sub d term. And then I know that this is going to be the damping coefficient, right? It's negative zeta times omega sub n. I can do a little bit of trig identities and say that the cosine of theta is equal to this part here, right? Over this part here. Or I can say the tangent is equal to the opposite over the adjacent. I mean, actually, no, let me back up. The cosine, let me erase that again. The cosine term is going to be equal to the adjacent over the hypotenuse. So the cosine of theta is going to be equal to j omega sub n if you do your math, what you're going to end up canceling out, and actually it's just a j, these term will cancel, and what I'm left with is that term is equal to zeta. So if you have a plot of a bunch of different points and you want something to have a certain damping ratio, you're actually looking for an angle. So you throw a line at that angle, and wherever that point intersects your plots, you actually use that, and then you know you have your damping ratio. Okay, so this will be a lot more useful when we look later on, but I wanted to include it here because we actually see where we can get the derivations, and it's just trig identities to get there. We can also do some adjustments to do peak time and settling time, and we can use those terms there. Just depends on what you want to do. So some tweaks, if you want to move your poles in a vertical direction, which means you're moving them up or down, you're going to get essentially more overshoot. But you'll notice that you have this envelope of your system. So its peak value looks to be the same, but your decaying exponential that you have overriding that sort of dictates where all that stuff happens. If you move a pole in the left or right direction, your frequency stays the same, but your overshoot increases or decreases. And if your poles move in this radial line, what does that tell you based on this previous figure? Yeah, same zeta, which means your percent overshoot isn't going to change. So this is the same height. Okay. But you'll also notice the further away that you get from the J omega axis, the faster it reaches steady state. So if you have a way of tweaking that pole and staying on that line, you can maintain your overshoot, but you can also have a system that reaches stability or steady state much faster. So if we have an example here, we want to find peak time, percent overshoot, and settling time from this following pole zero map. All we know is that we have two poles at -3 plus or minus J7. So our poles are -3 plus or minus J7, right? So the first thing we can do is we can immediately calculate what zeta is. So zeta here, which is equal to the inverse cosine of the opposite over the adjacent. So inverse tangent of 7/3 tells us I've got my percent overshoot of just under 4. And we know that omega sub n, or omega sub d, I should say, is equal to 7. So we can actually pull out what the natural frequency is just by using this formula here. Okay, we're back calculating it there. And now we have omega sub n. Now at this point, we can go ahead and calculate our peak time, pi over omega sub d. 45 milliseconds or 450 milliseconds. Our percent overshoot, now we know what zeta is equal to 26%. And our settling time is just 4 over that real part, which is our term 3 right there. Okay. Any questions?
We see that equation,
This one right here? No. Where'd you get it from? What is zeta equal to? What's that? Remember, we have 2 zeta omega sub n. What does that equal? That equals our A term, right? But we have to be careful. We need this in terms of what the real part is, right? For that real part. So what is the real part equal to? It's equal to -b, right? -b plus or minus b squared minus 4ac all over 2a, the square root. So this -b term is equal to -2 zeta omega sub n. And our, let's see, our zeta term is equal to our sigma over 2 omega sub n. And then we have to just go ahead and we substitute, let's see, we substitute this into here and we square both sides to get rid of the square roots. And we end up with that formula or that equation there. Okay, so that's where that equation derives from. Does your head hurt yet?
Yeah.
Yeah, this is tough stuff to get through, but the nice thing is, once you have this, you have a lot of design capability. And that's really what we're trying to do in this class is, again, live in the Laplace domain. So all these parameters here, we haven't gone back into the time domain at all, but we can do a ton of design just by looking at the system and analyzing it that way. I got 1 minute left. Any questions? Need some ice?
You have to pull it down. Get them.
Well, the next class you have with me won't be so crazy because we're just doing an exam review, so. All right, if there are no other questions, have a great day or a great weekend. And I'll see some of you in a little bit, or otherwise I'll see some of you next week. Take care, everyone.